Now we will be studying word problems that come from Chapter 8. Alright, there will be 2 videos over word problems from Chapter 8. So your heading today obviously is Word Problems, Chapter 8 Word Problems Part 1, and as always, I would strongly recommend that you include today's date so that your notes are organized. Alright, let's continue on. Obviously, because Chapter 8 is about logarithms and exponentials, we're going to be studying word problems that take that knowledge that you've learned and apply logarithms and exponentials to word problems. Now we're going to be looking at only 2 examples, so this video will not be that long. However, it will be packed with information, excuse me. So please take really good notes and pay attention, okay guys? Like always, I mean, you've got to learn the math, so let's get after it and let's work hard. The first problem that we're going to look at is about writing an exponential function. And then after you've written it or figured out what the function is, then you're going to use it to solve the problem. So here we go. I would encourage you to not copy this problem down, but instead put in your notes page 401, example 5. That is what I would put in your notes, okay? Page 401, example 5. Now, feel free to turn over there if you want to, or you don't have to. It's up to you. All right. Here we go. You purchase a new car for $20,000. All right. In 1990, the value decreases 16% every year. What will the car be worth in 1996 and 1998? Now, there is a long way to do this, where you take this number and take off 16%, then do it again, then do it again, then do it again, then do it again for 6 years. Then do it again for 2 more years to 1998. But that's a pretty long way to do it. And on a test or a quiz, I might give you something like this. I might say, what's the value of the car in 2035? Well, that means you'd have to find the percentage 45 from 1990 to 2035. You would have to take 16% off 45 times. Okay, so you do need to learn how to do this using exponential functions. Okay, so let's get after this now. First of all, I'd like you to forget this problem for a second and think of something else, would you please? I taught you this in a previous video. I taught you that. Let's pretend we're not dealing with a decrease problem. Okay, let's pretend we're dealing with an increase problem just for a second, okay? So forget this problem for a second, alright? And just listen to me. Now, let's say you have a $20,000 salary and your boss tells you he's going to give you a 5% raise, alright? Well, you would take 20,000 times 0.05 to see how much your raise is. And you would see it's $1,000, okay? Then you would add that back to the 20,000. And your new salary would be $21,000. Now, I taught you the other day, there's a faster way to do this, because it's an increase problem, because your salary is being increased. You can actually, instead of multiplying and then adding, you can take this percent and add 100% to it. And instead of using 5%, use 105%. Now you add 100 because it's an increase problem. So instead of taking 20,000 times 5%, you would take 20,000 times 105%, which is 1.05. Now guess what? If you take 20,000 times 1.05, you get 21,000, which is the same thing. But do not see how you cut a step out. Instead of multiplying by 5%, getting a number, and then adding it back to 20,000, you simply add one step. Take your salary times 1.05, okay? Well, this process is also true with decrease problems. Only instead of adding the percent to 100, you're going to subtract it from 100. So let's say you're not doing a good job at work and your boss says, or let's say you are doing a good job and your boss says, look, times are rough right now. I'm going to have to give you a 7% decrease, okay? Or a 7% cut in your salary. Well, you could take 20,000 times 0.07, and if you did that, you would get 1,400, okay? And then subtract that from 20,000 to find your new salary, or 20,000, and you would get 18,600. That's fine, but there's a faster way, because this is a decrease problem. Instead of adding 100% to this, you're going to subtract 100% or 7 from 100%, and you're left with 93%. Okay? Okay, so now take 20,000 times 0.93, and guess what you get? 18,600. That's a lot faster. It's one step. So I really strongly recommend this method here. Okay, if it's decrease, subtract the percentage from 100. If it's increase, add the percentage to 100. Okay. So having said that, now let's apply that to this problem. Okay. We're going to write an exponential function that will help us. Look, guys, you're starting off with 20,000. Okay, and every year you're multiplying by. Now remember, if it's a 16% decrease, then subtract that from 100, and what do you get? 84%. So that's what you're taking 20,000 times. 84%. Over and over and over. First year, second year, third year, fourth year. Every year you multiply again by 0.84. Well, don't you see the pattern? The pattern is 20,000 times what? 0.84 to a certain value. We'll call it x. Do you not see that? Look, guys, I don't know how many times I'm going to write this. So I put an x, and then y equals. That is a perfect model, guys. Come on, think about it. If I want to know the value of the car after 1 year, I put a 1 here and I evaluate it. If I want to know the value of the car 10 years from now, then I cross this off and put a 10. That's 0.84. 10 times, so 0.84 times 0.84 times 0.84 times 0.84 times 0.84, so on and so forth 10 times. So this is the perfect exponential model, and it's much faster than doing it over and over and over so many times. So there's your model. Now, the first question is, what will the car be worth in 1996? Okay, no problem. When was the car brand new? 1990. So in 1996, that's how many years later? 6 years later. So put a 6 here. So with your calculator, you want to type in 20,000, then parentheses, then 0.84, then close your parentheses, then put your arrow, and then 6. And you will get $7,025.96. We're just going to say, since we're dealing with a car, I'm not really worried about the pennies. We're going to say 7,026. That's the value of the car. It depreciated quite a bit, didn't it? It was worth this much. 6 years later, it's only worth this much. Now, let's apply this exact same model to the next question. Now they're asking, how much is the car worth in 1998? Okay, no problem. When was the first year it came out? Or when did you buy the car in 1990? So 8 years later, 1998. So now instead of having an X here, we're going to put an 8. So with your calculator, simply type 20,000, and then parentheses, and then 0.84, then parentheses, then put your arrow, and then an 8. And if you type that in correctly, you're going to come up with this: $4,958. $4,958. So that's it, guys. So you found the two values. This is what the car is worth in 1996. This is what the car is worth in 1998. Okay, guys, I hope that makes sense. Writing these exponential functions can really be helpful, guys. They can really be helpful if you know how to write them and then use them. Alright, moving on. The next word problem is about taking a logarithm, a logarithmic function, and using it to solve the problem. This one's much easier. And here it is. Now again, in your notes, I would just put page 415, example number 6. I would not copy this down, but that's up to you, okay? And actually, for this problem, you will need to turn to page 415, so I'm going to move on. You might want to pause the video. You have to turn to page 415 to do this problem, alright? And here we go. If you look at the top left of the page, it says, the Richter scale is used to measure the magnitude of an earthquake. Now, the magnitude R of an earthquake of intensity I is given by that model right there. So here's your model. R equals logarithm base 10 of I. I is your Richter scale number, and I is your intensity. So I'm going to continue to read from the top left corner, black bold print, top left corner, black bold print. Fourth line, fifth line down, it says, where the intensity is a measure of the wave of energy of an earthquake per unit of area. Alright, so there we go. This is the model we're going to use. R is the actual number on the Richter scale, this. It's a logarithmic expression. We're going to write it exponentially. So now we have this. We have, remember to write something from logarithmic to exponential. We would write it like this. This base gets put over here. The 8.3 becomes your power. And then I is all by itself here. So with your calculator, simply type in 10, arrow, 8.3, enter, and you will get 199,526,231.5. Now I'm not a scientist. I don't know a lot about what that means, but I know it is it's the intensity per unit of area that the earthquake took place in. All right. So there we go. So also think the other way, guys, would you please? If you know the intensity of the earthquake, you could put that in and get out the Richter scale, couldn't you? Sure you could, most definitely. All right, let's try letter B. Same model again, exact same model. The San Francisco Bay Area earthquake in 1989 had a Richter scale of 7.1. So for R right here, I'm going to put 7.1. And I'm going to find the intensity. So we should know what to do. We have a logarithmic equation. We're going to write it exponentially. So the 10 is the base. 7.1 is the exponent. And my eyes over here. So with your calculator, type in 10, arrow, 7.1. And you will get 12,589,254.12. So that is the intensity of an earthquake when the Richter scale is 7.1. Alright? So what did we learn here? Probably not a ton, except that we're learning how to apply these models to word problems. And by the way, this is pretty cool. This is all math and all science, guys, okay? I mean, these things that we take for granted, knowing the Richter scale, or knowing the what the earthquake, where the earthquake placed on a Richter scale, stuff like that. We use models like this, logarithmic models. Okay. Alright guys, I hope this video has been a help to you. If you have any questions, never hesitate to